Welcome to the Explainer. Have you ever walked out of a Cambridge physics exam totally exhausted and felt like the examiner was speaking a completely different language? You know the physics, right? You've memorized the formulas, you understand the concepts, but somehow, when you get that past paper back, the marks have just slipped right through your fingers. Well, today we are changing all of that. We are getting straight inside the examiner's head for the Cambridge Physics Alternative to Practical paper. And honestly, this strategy applies whether you're tackling syllabus code 0625, 0651, 0652, 5044, or even setting your foundation for 9702. To really understand the challenge we're up against, I want you to imagine two very typical physics students. We'll call them Alex and Sam. When confronted with a practical exam question, Alex completely overloads. Alex floods the page with every single raw physics fact they can possibly remember. Seriously, if a question asks about measuring a pendulum, Alex is out here writing a whole university-level essay on gravity, mass, and tension. But Alex completely misses the actual analysis the examiner asked for. The result? Red ink everywhere. Then there's Sam. Sam reads the question, thinks, "Oh yeah, I know this," scribbles down a quick, rushed one-sentence answer, and totally ignores the specific command word requirements. Sam is moving too fast. Both Alex and Sam are losing massive amounts of marks, but not because they don't know physics. They're failing because they don't know exam strategy. They don't know how the examiner thinks. Today, we are turning those red marks into green check marks. By breaking down past paper questions into repeatable, high-scoring skills, we're going to completely overhaul your approach. Okay, let's dive into this. Here is our 4-part playbook for dominating the exam. 1. Mastering precise measurements. 2. Planning flawless experiments. 3. Extracting data and rates. And 4. Evaluating experimental results. Starting right off with Section 1, Mastering Precise Measurements and How to Capture Exact Physical Properties. Now, you might be wondering, what is the alternative to practical paper actually testing? The examiners know you aren't physically in a laboratory doing the experiment. They get that. But they want absolute, undeniable proof on your paper that you understand exactly how to measure things accurately in a physical space. This is where top-tier students apply a mental framework I like to call PEEL. That stands for point, evidence, explanation, link. It is a game changer. I want you to put yourself in the shoes of a physicist holding a stopwatch. You are timing a pendulum swinging back and forth. The exam asks you to find the period of one single oscillation. So let me ask you, why on earth does the examiner insist that you measure the time for 20 whole oscillations only to divide that massive total time by 20 at the very end? Why not just measure one single swing and save yourself the hassle? If our student Sam answered this, Sam might just write, "because it's better," or "to make it accurate." If Alex answered it, Alex might write a massive paragraph on air resistance and the conservation of energy. Both of them completely miss the mark for this specific assessment objective. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, so here is the exact examiner-approved answer. To obtain a more reliable value for the period, let's apply our PEEL framework to understand the actual science of accuracy happening here, because you need to understand the why. Think about your body. When you press a stopwatch, your brain takes about 0.2 seconds to react to what your eyes are seeing. That is your baseline human reaction time. If a pendulum takes exactly 1 second to swing, and you have a 0.2 second delay starting the watch and another 0.2 second delay stopping the watch, your percentage error is absolutely massive. You could be up to 40% off the true value. But if you let that same pendulum swing 20 times, taking, let's say, 20 seconds total, your human reaction time error doesn't multiply. It's still only that exact same 0.4 seconds total for starting and stopping. When you do the math and divide the total 20 seconds by 20 to find a single period, you are also dividing that human error by 20. You are literally shrinking your biological delay down to a tiny, insignificant fraction of a percent. Taking multiple readings and averaging them directly neutralizes human reaction time errors. That is what the examiner wants to see you understand. And honestly, this brilliantly illustrates the visual and spatial awareness that examiners demand from you. Let's look at some other crucial accuracy secrets straight from the examiner's grading rubric. When you read a measuring cylinder, you cannot just say, "look at the water." You must explicitly state that you view the meniscus, that's the curved surface of the liquid, at eye level to avoid parallax error. When you're doing a ray tracing experiment with optics pins, you must clearly state that you place the pins a suitable distance apart. If you stick them too close together, a millimeter of misalignment creates a huge angular error by the time you draw the line across the page. When measuring a pendulum's length, you don't just awkwardly hold a ruler up in the air. No. You use a set square pushed flat against the bench to ensure the ruler is perfectly, exactly vertical. And when dealing with electricity and resistance wires, you must measure the length exactly between the inner edges of the two crocodile clips. Why? Because that is the only part of the wire the current is actually flowing through. You see what we're doing here? By stating these exact precautions, you are proving to the examiner that you know how to operate like a professional in a real-world lab. Moving on to Section 2, Planning Flawless Experiments. Let's look at the classic rubber band investigation. Okay, listen up, because these 7-mark open-ended planning questions can seriously overwhelm even the best students. Let's say the experiment asks you to investigate how strips of rubber of different widths stretch when they are loaded with weights. Sam, moving way too fast, might just scribble down, hang weights on the rubber bands and measure them. 0 marks for structure. Alex might write a massive essay on the molecular structures of polymers and Hooke's law. Again, totally missing the point. Instead, you need to decode the command words and use this exact 4-step blueprint to guarantee full marks every single time. Step 1. Explain briefly how to carry out the investigation. Keep it simple and physical. I will hang a rubber band from the clamp, measure its original length with a ruler, add a standard load, and measure the new stretched length. Done. Step 2. State the key variables that absolutely must be controlled. If you are comparing different widths of rubber bands, the original unstretched length of those bands must stay exactly the same. You have to isolate the variable you're testing. Step 3. Draw a table with column headings. Now here's a huge tip. You don't need to invent fake numbers. Just provide the headings with the correct units. Width of band with a slash and millimeters, and extension with a slash and centimeters. Step 4. Explain how to use the readings to reach a conclusion. I will plot a graph of width on the x-axis against extension on the y-axis to visually determine the relationship. If you follow these 4 steps, you instantly transform a messy, chaotic paragraph into a perfectly structured, full-mark response. Let's put this blueprint to the test, specifically focusing on Step 2, Controlling Variables. Imagine you are running a classic thermal physics experiment. You have 2 beakers of hot water. Beaker A has thick insulation wrapped all the way around its sides. Beaker B has no insulation, but it has a lid sitting on top. You want to see which one cools down faster. The exam question asks, what happens to your average cooling rates if you don't control the initial hot water temperature? What if, purely by accident, Beaker A starts at 83 degrees, but Beaker B starts way up at 90 degrees? Think deeply about the physics of thermodynamics here. According to the laws of physics, a hotter object naturally loses heat to its colder surroundings at a much, much faster rate than a cooler object does. So if Beaker B starts out significantly hotter, its initial cooling rate is going to be extremely rapid, completely regardless of whether it has a lid on it or not. So the exact, concise answer you must provide to get the mark is, results cannot be accurately compared. If you start your timers at different temperatures, you completely change the initial slope of the cooling curve. It becomes entirely impossible to fairly compare the insulated beaker with the lidded beaker because you have introduced a massive, secondary, hidden variable into your experiment. This right here is why stating your controlled variables is absolutely critical to getting top marks. Examiners are actively hunting for students who realize that experimental fairness is the absolute foundation of good physics. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Let's push forward to Section 3, Extracting Data and Rates. This is all about turning raw meter readings into usable physics. All right, welcome to the interactive workshop part of this explainer. This is where you must prove you can turn raw numbers into a clear scientific story. Let's do a quick data scan challenge. Look at the trend in this data table. We have time in seconds, Beaker A temperature, and Beaker B temperature. First thing, look right at the column headings. They perfectly follow the Cambridge format, the physical quantity, a forward slash, and then the unit. Time/S, temperature/degrees Celsius. Never, ever forget your units in table headings. Now let's scan the data. At time 0, Beaker A starts at 83.0 degrees. After 180 seconds have passed, it drops down to 68.5 degrees. Beaker B starts at 86.0 and drops to 78.5. A quick mental calculation tells us Beaker A lost 14.5 degrees in total. Beaker B only lost 7.5 degrees, so obviously Beaker A cooled much faster. But listen to me carefully. On the actual exam, you cannot just write Beaker A cooled faster. That's not physics, that's observation. You need to calculate the exact numerical rate.
Very often, the exam will hold your hand and provide you with a specific formula. Here, they define the average cooling rate, which they call X, as the total change in temperature from time 0 to 180 seconds divided by the total time elapsed, which is 180 seconds. So for beaker A, we take 83.0 minus 68.5, which gives you a temperature drop of 14.5. Then you divide that 14.5 by 180. That gives you your exact numerical rate. But here is the massive trap that catches so many students. Our student Sam does this calculation, gets the number 0.0805, quickly writes it down on the answer line, and jumps straight to the next page. What did Sam do wrong? Sam just lost an easy mark because Sam forgot the unit. The unit for cooling rate in this specific experiment is degrees Celsius per second, written as degree C/S. And the best part? The formula literally tells you exactly what the unit is if you just look closely. It's a temperature unit divided by a time unit. Don't leave money on the table, always check your units. Now, sometimes the formulas the examiners throw at you look a little weird. They might seem like they belong in a different syllabus entirely. Take a look at this constant from a past paper where students were asked to calculate the volume of a cylindrical cup using only its diameter and its height. The formula provided on the exam paper was V equals 0.785 times d squared times h. So, where in the world does 0.785 come from? It looks like a random magic number. Well, let's break it down. We know the volume of a standard cylinder is pi times the radius squared times height. But in the lab, you can't easily measure the radius of a cup. You measure the full diameter, d, with a ruler. The radius is just d divided by 2. When you square that fraction, you get d squared over 4. And what happens when you take pi, which is roughly 3.14, and divide it by 4? You get exactly 0.785. Now here is the secret. You do not need to derive this in the middle of the exam. The examiner will sometimes provide unique, pre-simplified equations you've never memorized. Your only job is to stay calm, confidently plug your accurate data into them, and ensure your final answer is rounded to the correct significant figures. Let's switch gears and look at spatial awareness in electrical circuits. This is where your time management matrix comes into play. You need to spot these differences instantly. Comparing lamps wired in series versus parallel changes absolutely everything about how you extract data. Look at the series circuit on the left. There is only one single pathway for the electricity to flow. The ammeter is in the main line, measuring the total circuit current, and that current is exactly the same everywhere. The voltmeter is placed widely across both lamps, measuring the total combined potential difference. But look at the parallel circuit on the right. The current splits at the junction. If the examiner asks you to position an ammeter to measure the current flowing through just one specific lamp, you absolutely cannot put it next to the battery. You must physically draw it on the specific branch containing that one lamp, and the voltmeter must be placed directly across the parallel branches. The fundamental physics rule here is that charge is conserved, but it takes multiple paths. Mastering this specific spatial awareness on your circuit diagrams is absolutely guaranteed to boost your grade. If you wired this wrong in your head, the examiner knows immediately. Finally, we reach Section 4, Evaluating Experimental Results. This is the ultimate test of your understanding. This section is where you must transition from simply doing the experiment to aggressively judging it. Look closely at this quote. State whether the readings support this suggestion. Justify your statement with reference to the results. I need you to burn this exact phrase into your memory right now. It is the single most common command phrase you will face in the alternative to practical paper. It demands that you explicitly link a theoretical physics rule back to your actual calculated numbers. You absolutely cannot just write a lazy, yes, they support it, and move on. If a hypothetical student in the exam suggests that doubling the voltage across a wire should perfectly double the current, you must formulate your answer like this. Yes, the readings support this suggestion because when the voltage increased from 2.0 volts to 4.0 volts, the measured current increased from 0.5 amps to 1.0 amps, which is a proportional doubling, within the limits of experimental accuracy. Listen to me, that phrase, within the limits of experimental accuracy, is your absolute best friend in this exam. Use it. Let's look at two distinct classic examples to prove that examiners will repeatedly ask you to verify a proposed rule against your gathered data. First, in a standard series circuit, does the total source voltage, Vs, truly equal the voltage of lamp X plus the voltage of lamp Y? Well, in a perfect, frictionless textbook world, yes, it does perfectly. But in your messy lab data, Vs might be 3.0 volts, and Vx plus Vy might add up to 2.9 volts. Are they equal? Cambridge says yes, they are considered equal within the limits of experimental accuracy. You get the mark for recognizing that tiny physical losses happen.
Second example. In a glass block ray tracing experiment, a student suggests that the emergent angle, alpha, should always perfectly equal the angle of incidence, I. If your angle of incidence is exactly 50 degrees, but your protractor measures an angle alpha of 52 degrees, you must be bold and state, no, the results do not support the suggestion because 52 degrees is clearly not equal to 50 degrees and a 2-degree difference is significantly beyond reasonable experimental error. You have to step up and be the strict judge of the data. Now, evaluating an experiment also means spotting the physical flaws in the setup itself. Why might your voltage readings not add up perfectly in that circuit? One of the most powerful, high-level answers you can give in any electricity practical question is identifying the heating of the resistance wires. Think about it. As electrical current flows through a metal wire, the moving electrons constantly collide with the atomic lattice of the metal. These constant collisions generate thermal energy, heat. As the temperature of the wire increases, the metal atoms vibrate much more violently, which physically obstructs the electrons even more. This means the actual electrical resistance of the wire increases while you are testing it. So if you just leave the circuit switched on for 3 straight minutes while you write down readings, your resistance values are going to completely drift away from their true values. This is why a top-tier guaranteed mark precaution is to write, I will open the switch between taking readings to prevent the resistance wires from heating up. Bam! You just proved to the examiner that you deeply understand the invisible physical processes happening inside the experiment. All right, we have completely broken down the playbook. We've covered mastering precise measurements, flawless planning with the 4-step blueprint, extracting data without losing unit marks, and deep evaluation of flaws. By utilizing our complete system, number 1, command word decoding, number 2, Peel framework application, and number 3, the time management matrix, you are absolutely guaranteeing yourself top marks in this paper. Students who implement these physics strategies see an average improvement of 2 whole grade boundaries. But that only happens if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and tell us the biggest challenge you're currently facing. Our team responds to every single comment. Like and share this video with a study partner who needs it. Ace the Exams, your Cambridge success starts here.